Welcome back. In the previous session, we have completed the fundamentals of the signals and system. So in that we have seen basic signals like impulse, step, ramp, parabolic, like that. And we have seen basic operations on the signal. Then how to represent the signals in terms of step and ramp signals. That is also we have seen. Okay. So that is about the first subtopic, which is nothing but fundamentals of the signal. Next subtopic, which is a classification of signals, means based on the various parameters we can divide or we can classify the signals into different categories. So today our topic is classification of signals. In that, the first classification what we are seeing is nothing but real and complex signals. The first classification what we will see is real and complex signals. Real and complex signals. Let's say, when can we say a real signal? When can we say a complex signal? Okay. First, try to understand. If you take a signal, it's all about the amplitude. For all the time instants, whatever the time instant you take, it doesn't matter. If you always get the value of the signal or value of the function is a real value. That means if the signal is said to be real, if and only if its amplitude has to be a real value for all the instants of time, then we can say it is nothing but real signal. Next, what do you mean by a complex signal? So the definition is tricky here. For any instant of time or at least one instant of time, if the amplitude of the signal is a complex, that is enough to say the signal is a complex signal. So to say a real signal, we have to check each and every time instant. But whereas to say a complex signal, at least one time instant is enough to say it is a complex signal. That's what the meaning of it. Suppose let's say the definition I am writing here, real signal. Real signal. What is a real signal? A signal is said to be real if its amplitude or value is real for all the values of t. For all the values of t. For all the values of t. Suppose let's take some examples you can understand. X of t is equal to sine 10t. If you see, whatever the time instant you take, it doesn't matter, its value is always lies between -1 and +1. Okay, so because the amplitude is 1, so it is lies between -1 and +1. Its value will never go to a complex value. Its value never become a complex value. So we can simply decide, yes, this signal is a real signal. I hope you understood. Some more signals, let's say u of t. If you observe carefully u of t, have you ever seen a complex number in u of t? No, only I may see 0 or I may see 1. Okay, other than that we won't see anything. R of t, e power, let's say 2t, etc. These are the signals what we can decide as a real signals. I hope you understood real signals. Okay. Next, what do you mean by a complex signal? Complex signal. We can say a signal is a complex signal if its amplitude is complex for at least one value of t. Okay. So if its amplitude is complex for at least one instant of time, at least one instant of time. Okay, let's see example, you can understand. If I take x of t is equal to e power, let's say jt. So from the Euler expansion, it can be written as cos t plus j sin t. This can be written cos t plus j sin t. Euler expansion, we know that e power j theta is equal to cos theta plus j sin theta. So from this, if I substitute t is equal to 0, then what is x of 0? Cos 0 plus j sin 0, this is nothing but 1. So its value is real. Can I say it's a real value, real signal? No, I cannot say it's a real signal because we have tested only one value of t. Let's say one more thing. Let's say t is equal to pi by 2. Then we can get x of pi by 2 is equal to cos pi by 2 plus j sin pi by 2, which is nothing but 0 plus j, which is nothing but a imaginary value or complex value. Yes. So at least one instant of time, if the amplitude is complex number, then we can decide the signal is a complex signal. So this is the thing what we have to check. So it's not necessarily all the values of t, it has to be complex. For any instant of time, if it is complex, then we can decide it's a complex signal. So many people argue with me that, sir, we know that complex numbers, real numbers, every real number is a complex number. We know that because complex numbers is a superset, whereas real numbers is a subset. So from that basis, can I say that every real signal is a complex signal? Absolutely not. You cannot say that because these are mutually exclusive. These are mutually exclusive. Either they have to become a real signal or they have to become a complex signal. There is no way you can say a real signal is a complex signal. No, you cannot say that. They can be a real or they can be complex. That's the only way we can say. So don't bring the number system into the signals here. So numbers, real numbers and complex numbers is a different concept, and a real signal and a complex signal is a different concept. Don't club them. Okay, take it. Second classification of the signal, which is deterministic and random signals. Random signals. So on what basis we can decide whether it is a deterministic signal or random signal? We have to check it out. Okay. Okay. Listen carefully. When can we say a signal is a deterministic signal? So simply the word itself saying that determine. That means if I can determine the signal value, that means the signal amplitude for all the instants of time. That means if I could say what is the value of the signal at each and every instant of time, then we can simply say the signal is deterministic signal. I hope you understood. For all the values of time, you have to know what is the amplitude of the signal. Then we can call that signal is a deterministic signal. Or there is another definition for deterministic signal is, if you could write or if you can write the signal in the mathematical expression. That means if a mathematical expression is possible for any signal, then we can call that signal is a deterministic signal. That's what it is. Okay. So I am just taking deterministic signal. Deterministic signal. If the value of the signal, a signal is said to be deterministic if the value or amplitude both are same, value of the signal can be determined for all the values of t, for all the values of t. Then we can say that signal is a deterministic signal, or we can write mathematical expression is possible if mathematical expression is possible. Expression is possible. Either of the definitions is okay. Okay. Let's see examples. You know well-known examples. Let's say x of t is equal to sine 2t. If I give a time instant, let's say t is equal to 2 seconds, can you tell me what is the value of the signal? Yes, sine 2 into 2, that is nothing but sine 4. That means in the radians. Yes, we can say the value of the signal at each and every instant of time. U of t, r of t. So whatever the signal we are seeing, so till now, they are all can be expressed in a mathematical form. So till now, whatever the signal we have seen, that is all are deterministic signal. Suppose if I say e power jt, is it a deterministic signal? Of course it is a deterministic signal. Yes, this is the mathematical expression of the signal. Suppose I can write x of t is equal to e power jt. Yes, this is the mathematical expression. And you can say the value. I am not saying that value has to be a real value or complex value. It can be anything. We don't care about that. Maybe real, maybe complex. It doesn't matter for us. But you have to say the value. That's only the thing. So if you can say that value may be real or complex, it doesn't matter. Then we can say that is a deterministic signal. Yes, e power jt is a complex signal, but it is a deterministic signal. That's what the meaning of it. Okay, so these are the deterministic signals. Then what do you mean by random signal? Random signal. The definition is simply opposite. That means if the value of the signal cannot be determined for all the values of time, and mathematical expression is not possible. So simply you have to write the definition in the opposite manner. So a signal is said to be random signal if the value of the signal cannot be determined for all the values of t. And if mathematical expression is not possible, then we can call that signals as random signals. Can you tell me some examples for random signals? Yes, definitely. Noise, my voice, even voice is also called as a random signal, etc. Because you cannot say these values for all the values of time. You cannot say that. So that's why it is called as noise, voice. These signals are random signals. Okay. Sir, if mathematical expression is not possible for the random signals, but maybe if you are a electronics and communication student, you might study the random signals in the communications in the chapter called as noise and random process. Sir, we have seen the mathematical expression for random signals also there. No, you haven't seen the random signals mathematical expressions there. But what you have seen is a probability approach. Remember, random signals mathematically analyzed. Random signals can be mathematically analyzed. But we have to go for probability approach. Probability approach is never going to be correct. So it's just a predictions, expectations. So I can say 99%, 100%. So 100% is the only that is can be trusted. If you say anything other than that, 99%, 99.999%, still there is a chance that it may go wrong. So probability approach is used for the random signals analysis. Understood? So I am writing that random signals can be analyzed by probability approach. Probability approach. This is not a correct approach. Probability approach may not be, expectations, variance, like that. Okay. Probability approach. Okay. So you can write the definition of random signals just opposite to that and take these examples, and random signals can be analyzed by probability approach. Okay, take it. Well, anti-causal, and non-causal signals. Non-causal signals. This is the next classification what we have to see. Okay. So mathematically we can say causal signal, anti-causal signal, like that. Okay. So mathematically we can say these signals in a easy manner. Let's see. Suppose if a switching action is happened, so from that point you know all the values of the signal. That means you can see directly, yeah, after a switching action you will be there. So because you are the only person which is switching action has done. So you can understand what are the values of the signal because you are seeing the signal. That means after the switching action, if the signal is existing, then we can call that signal is a causal signal. So let's say when you enter into a room, the signal is already there. That means you don't know what was happened in the previously. Then those are nothing but non-causal signals. So mathematically this is going to be very easy. So than the definition wise, let's see how we can say. If a signal x of t is equal to 0 for t less than 0, that means for a negative values of time, the signal should not exist. That means we can take t is equal to 0 is the switching action point. So that before that we don't know that signal. That means the signal has to be 0. Means we are taking the signal value is equal to 0 for t less than 0. Then we can call that signal is a causal signal. In the similar way, in the discrete time case, x of n is equal to 0 for n less than 0. Then we can say these signals are causal signals. Causal signals. Causal signals. Next, anti-causal. That means just opposite to that. Suppose if the signal is not existing for positive values of time, t greater than 0. If I take x of n, here is the thing you have to remember. For n greater than or equal to 0, because let's see, here strictly greater than 0, but here greater than or equal to 0 we have to consider, because let's see, for n less than 0 means what is the starting point? N less than 0 means next point is nothing but below 0 we are having -1, -2, -3 like that. So that means the signal has to exist from 0 to infinity. So it should be 0 means the signal has to exist from 0, 1, 2 like that. So what is the opposite for that? It has to exist up to -1 only. That means after 0, that means from 0 onwards, 0, 1, 2, 3, those values has to be 0. That's what the difference between them. So please be careful with the x of n signal definition. Then we can call this is a anti-causal. Anti-causal. If you take the combination of these two, that means for a positive values and negative values the signal exists, then we can call that is a non-causal signal. So I am writing that if the signal exists for both positive and negative values of t, then the signal is non-causal signal. Non-causal. So just see some examples you can understand easily. If I say examples, u of t. So continuous time case. This is how it look like. What kind of signal it is? Because there is no amplitude for t less than 0. That means the signal does not exist for t less than 0. So whenever the signal is absent for t less than 0, that is called as causal signal. Causal. Next, u of minus t. U of minus t. That means it is existing only up to 0. That means for a positive values of time, the signal does not exist. Then we can call it is a anti-causal. Opposite to that, anti-causal. That is a anti-causal signal. Suppose if I take u of n, u of n, how it look like with respect to n? 0, 1, 2, like that, and so on. So from the definition, for n less than 0, that means minus 1, minus 2, minus 3, for those values the signal does not exist. So it is again a causal signal. Again it is a causal signal. Next, if I take u of minus n, then how it exists? U of minus n means for 0 its value is 1, minus 1 its value is 1, minus 2 its value is minus 1, and so on it will go. So if you observe carefully, from the definition of anti-causal signal, the signal should be absent for 0 onwards, means 0 also should not be there. But here if you observe carefully, u of minus n, it is having a 0 amplitude. That means n is equal to 0, we are having an amplitude. So the signal is existing for n is equal to 0 also. So it is not coming into the category of causal signal, it is not coming into the category of anti-causal signal. So we can say this is a non-causal signal. Non-causal. Be careful with this one. Non-causal. If I take another example, u of minus n minus 1. We already know it is existing from minus infinity to minus 1, minus 1, minus 2, like that, and so on. At 0 its value is 0. Now it will come into the category of anti-causal signal. Anti-causal. If I take another example like this, u of minus t, let's say plus 2. We know how to draw the signal, continuous time signal. It is existing up to 2. So the signal is existing for positive values and negative values of time. Then we can call this is a non-causal signal. It is non-causal. Okay, take it. Non-causal signal. Take the notes. Next classification of the signal is a right-sided and a left-sided signal. Right-sided and left-sided signal. Okay. First, to classify into right-sided and left-sided signals, the signal must be infinite duration. That means for a finite duration signal can never be classified into right-sided and left-sided signals. They must be infinite duration signals. Okay. So let's say infinite duration signal means if you take a signal, so it's a graphical, it is going to be easy to explain. So I am going with that. Let's say if a signal exists in this manner. So remember, first signal must be infinite duration. Signal must be infinite duration. This is the prerequisite condition. So this condition has to be satisfied at any cost. Now, if you observe carefully, the signal is starting at some point. We don't know. So that is not important for us where it is starting, whether it is a positive value, negative value, I don't care where it is starting. But it is going to infinity, means t value is tending to infinity in this direction. So it will reach us to infinity. So the signal t value reaches infinity. So it is starting from here and it will go to infinity like that. Then we can call this is a right-sided signal. It is a right-sided signal. Suppose if I give like this, where it is starting it doesn't matter. Where it is starting it doesn't matter. Where it is going, that is very important. So it is also a right-sided signal. Next, suppose if a signal is existing like this, so it is going to infinity in the negative direction. So I can say it is a left-sided signal. Left-sided signal. Suppose if I say still it is going to infinity in the negative direction, so it is a left-sided signal. What if the signal is going to infinity in both the directions? Suppose if you take a simply a DC signal, it is extending from minus infinity to plus infinity. So it will go to infinity in this direction, it will go to infinity in this direction, both the directions. Then we can call it as a two-sided signal. Then it is a two-sided signal. Two-sided. Understood? So let's say e power, let's say 2t or minus 2t u of t. How it look like? This is how it look like. We already know this. So what kind of signal it is? It is a right-sided signal. So it is a right-sided signal. I hope you understood. Okay, take it. So from this, can I do one thing? Can I say or can I observe something? Suppose a signal is a infinite duration signal. What if the signal is causal signal? Can I call all infinite duration causal signals are nothing but right-sided signals? Why? Simply. So take this as an example. Is it a causal signal? Yes, definitely. Is it an infinite duration? Yes. So can I call it as a right-sided signal? Of course it is a right-sided signal. So I can say all causal signals are right-sided signals. So I am writing that note point. All causal signals are right-sided. Right-sided. Okay, take it. Next, bounded and unbounded signals. Next classification, bounded and unbounded signals. Bounded and unbounded signals. Okay. Try to understand this. It is very, very important. We will keep on seeing this in the stability also. Bounded and unboundedness. Suppose if you take a signal, if you observe the signal amplitude for all the values of time, whatever the time instant you take, it doesn't matter. For all the values of time, the amplitude should never go to infinity. Should never go to infinity. That means its amplitude always has to be some finite values. So it is not a constant value. It can be any finite value, but it has to be a finite value. Then we can say that signal is a bounded signal. That is as simple as that. Suppose at any instant of time, whatever may be the time instant, at least one instant of time, if the amplitude goes to infinity, then we can call that signal is an unbounded signal. That signal is a unbounded signal. Okay. So I am writing the definitions here. Bounded signal. bounded signal. The amplitude should never go to infinity. Go to infinity. This is the verbal definition of a bounded signal. Then how we can say the same bounded signal mathematically? How we can represent a bounded signal mathematically? Suppose if you take the magnitude of the signal x of t, the magnitude of the signal x of t, its value should be always less than or equal to some maximum value. Less than or equal to some maximum value. So this is the definition of bounded signal, and this m value should never be infinity. That means this value should never go to infinity. That means it is always less than infinity. So this is the mathematical definition of bounded signal. Okay, let's see. Then what is the unbounded signal? The amplitude has to be infinity for at least one instant of time. Okay, so that is called as unbounded signal. Okay, let's take some examples so that you can understand which are bounded, which are unbounded. First question, u of t. U of t, is it a bounded or unbounded? So just check it out. U of t. So never observe the t. So some people will argue me, sir, t is going to infinity in this direction. So can I say it is an unbounded signal? No, it is not about the time axis. It's all about the amplitude. So are you saying infinity amplitude? No, its maximum value is 1. Then we can say it is a bounded signal. Bounded. Next, second one, delta t. If you observe carefully, delta t, at t is equal to 0, its value is infinity. The one what we are writing is the area under the impulse function, but what is the amplitude of the signal? It will go to infinity. So it is a unbounded signal. It is a unbounded. Unbounded. Next, third example. If I take delta n, the same definition goes for continuous time case and discrete time case also. For a discrete time case also the same thing. Mod x of n has to be less than some maximum value which is less than infinity. If you observe carefully, delta n, its value at 0 is not equal to infinity. Its value exactly equal to 1. Then it is a bounded signal. So remember, delta t is a unbounded signal, whereas delta n is a bounded signal. It is a bounded signal. Next, suppose if I take r of t, how it look like? R of t, it is go in this direction. Slope is equal to 1. Now if you observe carefully, if t value increases, definitely its amplitude going keep on increasing. At t tends to infinity, its amplitude is also tending to infinity. Then we can simply say, yes, this amplitude goes to infinity. So it is a unbounded signal. It's a unbounded signal. Unbounded signal. Suppose if I take next, e power 2t. It's a growing exponential. So we don't have any u of t, u of minus t terms. That means it is existing from minus infinity to plus infinity. So it will go in this direction. So is it a bounded or unbounded function? So it is definitely unbounded, because when t tends to infinity, its value goes to infinity. So it is also unbounded. Next, some people think that e power, let's say, minus 2t, it's a decaying exponential. Some people may say that, sir, it is a bounded function. No, because if you observe carefully, the function looks like this. When t value tends to minus infinity, its amplitude goes to infinity. Then we can say it is also unbounded function. It is also unbounded function. First take them, then we will see the remaining example. E power minus 2t u of t. E power minus 2t u of t. So it is a decaying exponential, but we have to consider only for positive values of time because it is multiplied with u of t. Then how it look like? So you tell me, is it a bounded function? Yes. In this case, its value is bounded because the maximum value is 1. So every value is below than this. So definitely it is bounded. It is bounded. Next, what if I take e power minus 2t u of minus t? That means it is a decaying exponential, but we have to consider only negative portion. That means for negative values of time only we have to consider it. Then how it look like? Decaying exponential means with the time progresses it is decaying, but it is existing only for negative values of time because it is multiplied with so here when t tends to minus infinity, its amplitude goes to infinity. So we can call this is a unbounded. Take it, unbounded. Please make the notes simultaneously because we don't have much time. Next, e power, let's say 3t u of t. So it's a right-sided signal but growing exponential. So still it is a unbounded function because at t tends to infinity, it is infinity, unbounded. It is also unbounded. Next, e power 3t u of minus t. That means it's a growing exponential, but we have to consider only for negative values of time. So what kind of signal it is? So it is a bounded signal. Okay, take this.